Hello there, children. Today we are going to work on our Chapter 6 review. Oh, happy days are here again. So, with this, we're going to go over the review together. Now, the first thing here, if you look, is we have this squared. Now, it's simplified. Your answer should contain only positive exponents. So, when you have that x squared there, and you have the x squared and the y to the thirds inside, when you have a power to a power, you're going to multiply because sharing is caring. So we're going to share that 2 with all of those exponents. Now, you multiply. When you have a power to a power, you multiply. That's how we get an x to the 4th, a y to the 6th, an x to the 8th, and a y to the 4th. 2 squared, because that 2's exponent is 1, remember. There's a 1 out in front of that 2. Now, and there's a 1 in the exponent. So what I'm going to do when I get this is I have an x to the 4th and an x to the 8th. That makes an x to the 12th. There's 4 x's, there's 8 of them, that makes 12 of them. Then I have a y to the 6th, y to the 4th, that makes 10 of them. Oh, happy days are here again. Now the second problem, your answer should contain only positive exponents again. When I have that 2 and I share it here, I get a u to the 8th, a v to the negative 4th, a 2 squared, and a u squared. Simplifying u squared, u to the 8th, makes u to the 10th, and you think you're all hunky-dory, peachy keen, but oh no, there's a negative 4, and the direction said your answer should contain only positive exponents. So when an exponent is sad and negative, it goes somewhere else to become happy. And by goes somewhere else, I mean the fraction flips and it becomes positive. Oh, happy days are here again. Oh yeah. I have just a u, I have a v to the 4th, I have a 4. All exponents are positive, and there's no other simplification to be done. I'm good. Here, interesting idea. I again have to distribute the 2 as such. Now, there's a negative exponent. It's sad. It moves up and becomes happy. Then I have a u up top and 2 u's in the bottom. It's going to leave me with a u in the bottom. Or you can use your quotient property, 1 minus 2, which makes a negative 1, and that goes in the basement then. The v to the 6 is nothing to combine with. And a 2 divided by 2 squared, which is 4, 2 divided by 4 is just 1 over 2. So there's my final answer. And if you think about it logically for the u's, I know it might be a little confusing to some people. Look there, I have 1 u up top and 2 u's in the bottom. One of the u's up top kills one of the u's in the bottom, leaving me with a u on the bottom. Here, distributes everything, because sharing is caring. That makes 4 times 3 is 12. Negative 2 times 3 is negative 6. That makes an 8, because it's 2 to the 3rd. And that makes a 12. Now, again, we go, hey, I want everything to be positive. That y to the 6th isn't positive. Drop it down there and make it positive. Y to the 6th times y to the 12th. There's 6 y's, there's 12 y's, there's 18 y's total. Moving on. Here's my suggestion, folks. This is even for myself. I make careless mistakes sometimes. It happens. So what I'm going to do here first is I'm going to distribute the negative, making it negative 7n, negative 8, negative 6n squared. Okay, negative 6n, negative 2, and a positive 3n squared. Therein lies the rub, folks. You got to be careful because you're subtracting this entire trinomial there. So if you drop a negative sign by accident or forget to distribute, because sharing is caring, then you really don't care about all those terms. And we're all about caring and equality here in math. So what you've got to do is share it with everything. And then from here, it just becomes a game of combine your like terms. Notice all the highlighted things in blue. 3 minus 8 minus 2. Negative 7. That's negative 8n minus 7n minus 6n, negative 21n. Negative 2n squared minus 6n squared plus 3n squared, negative 5n squared. Now, I put it in this order. I didn't say put it in standard form. This is standard form because it is in decreasing order of exponents. If you have it not in this order, that's okay, provided I don't actually tell you put it in standard form. Same thing here, folks. Distribute that negative. It makes a big deal right here because it makes it positive. That's the biggest trick, is if you don't distribute the negative to everything, you're more likely to make a mistake, and nobody wants that. So you really got to be careful and clear and concise and make sure you distribute the negative. Now, if it's a plus sign, just drop your parentheses and you're good to go. But these subtractions are what I'm worried about. And then from there, it's combining your like terms. Notice how I don't add my exponents there, because we don't add exponents. Think about it. I have 4 apples minus 3 apples minus 6 apples. I don't get like apples cubed or apples squared. I just get apples. Units stay the same. All right, this one. Now, I showed you the distributive method here. In class, I have shown the rectangular method. I don't tell you how you have to do it, so whatever floats your mathematical boat. Rectangular method, for those of you, is probably a little bit easier and probably nice to do, so go ahead and do that. Distributive method, if you like writing it out in one big long string. Also, whatever floats your mathematical boat. The big trick here is that's a -2 there, so that's going to flip all those signs around. And then from there, it's a game of combining your like terms. Same way here. Again, you could use the rectangular method if you want. If you don't, distribute that x to all those terms. Distribute the -5 term. Nope. Sound effects optional. And then just simply combine your like terms. This one, factor each completely. Alright, this is a 4-term polynomial. And we talked about what we do with 4-term polynomials. Now, as I look at that, 4-term polynomials, we factored by grouping. Now, when I group this thing, I am going to do the following. I'm going to group the first 2 and last 2. Those aren't my binomials for my final answer, by the way, just so we're all clear. Now, what I'm going to end up doing is I'm going to pull out the GCF out of the first 2 items, which is 8x squared. And I ask myself, what times 8x squared gets me 56x to the 3rd? If I don't know that off the top of my head, I simply divide 56x to the 3rd by 8x squared. And I do this at 7x. And I do the same thing for 32x squared. Now when I do that, I have that binomial left. It's 8x squared times the binomial 7x minus 4. Then I go to the next 2 terms and go, what do they have in common? They have nothing that I can pull out of them except a 1. Yank out that 1, because they really always do have a 1 in common. It might not be helpful for GCF sometimes, but in this case it is. And then I go through. Now look, I have a 7x minus 4 in both the first term and last term. I yank that out, and I'm left with 8x squared plus 1. You could write it in either order, it's fine. Now, when in doubt, you FOIL it out. So I know that if I FOIL that, I will get back to my original answer. I'm done there because I cannot factor that any further. A reminder, if you can factor it further, let's say you got one of the factors being x squared minus 4. That's the difference of squares. So you might have to go a little further. In that problem you would. In this problem you don't, because I can do nothing different. Moving on. The same thing here. I'm going to factor by grouping. So when I do that, I group the first 2 and last 2 together. I pull the GCF out of the first 2. I look at 35 and 40 and realize I can pull out a 5. And look at m squared and m to the 3rd and realize I can pull out an m squared. And then I ask myself, what times 5m squared gets me 35m to the 3rd? That's 7m. What times 5m squared gets me 40m squared? That's an 8. And I look over here to these 2. What do they have in common? I can pull out a 4. And I'm left with 7m plus 8, excuse me. Now, both of these items have a 7m plus 8, so I yank that out. And I'm left with the 5m plus the 4. Or I could write it as 5m squared plus 4 times the quantity 7m plus 8, excuse me. Both are acceptable answers because multiplication is commutative. Problem 11 is a x to the 4th minus 7x squared minus 30. Now remember, x to the 4th is really x squared squared. So it's still factoring like we used to, only now the terms instead of x's in front here are x squareds, which is really nice. So I need to find 2 numbers that multiply to negative 30, but add to a negative 7. That would be negative 10 and a positive 3. You don't believe me? When in doubt, you FOIL it out. And you're good to go. Moving on. End behavior. It's what's happening at the end of the polynomial. Now, here, I always look at the biggest power I've got. The biggest power here is an x to the 5th. So I want to know what happens as x goes up, or it moves to the right. So I put large positive numbers, 100, 1,000, million, 2 million, a trillion, and take them to the fifth power. A positive number to the fifth power is going to yield me a positive. So the more I go to the right, the more positive number my number gets, or it goes up. So it's going to rise as it goes to the right. Conversely, put a negative in, like negative 20, negative 50, negative 1,000, negative 2 million, whatever. You take a negative to the fifth power. A negative times a negative is a positive, times another negative is negative, times another negative is positive, but times that fifth negative again is going to be negative. A negative to the fifth power is negative. Therefore, as I go to the left, I'm going to go down because I'm getting a negative value. So as I go to the left, I'm going to go down or fall. So I'm going to fall to the left and rise to the right. That would be my solution to the problem. You just remember that rising means go to the right, or go to the right and go to the left. You just realize that up is rising, down is falling. That's the big trick there. Now, this is good old-fashioned long division. I have to use long division here simply due to the fact that this is a trinomial, and that's an x squared. Thus, synthetic division, which requires a binomial of coefficient 1, exponent 1, out of the window. Synthetic's out. Not an option for me. Bummer. So what I do is, I take the biggest item I have, my divisor, and I look at this right here, this 3x to the fourth, and I ask the x squared, hey x squared, it goes, yeah, what's up? What could I multiply you by to make you that big, to make you a 3x to the fourth so I can cancel that out? So take 3x to the fourth and divide it by x squared, you're going to get 3x squared. And the x squared goes, listen, if you multiply me by 3x squared, I'll be big enough to crush that thing. So I do that. But because sharing is caring, I multiply the rest of this trinomial, or whatever I have out here, by 3x squared and get this. And then I subtract. Now notice here, I put a placeholder. That's simply to keep my work logical. You do not need a placeholder in long division, but it is an absolute must and necessity for synthetic division. So I do that. Boom, cancel it out. The 3x to the fourth, goodbye. That's what I wanted. So now I'm left with this. The other two numbers drop on down. And so I go again and ask the question. Now, the biggest thing I have left is a 6x to the third. I go to x squared and go, hey x squared, what's up, bud? What do you need to get multiplied by to be as big as that? So divide 6x to the third by x squared if you don't know. It's 6x. So the x squared goes, listen, if you multiply me by 6x, I'll be big enough to crush that thing. So I do that. And because sharing is caring, I multiply the entire trinomial by that. Subtract again. Rinse and repeat the process over again. What times x squared gives me 13x squared? A 13. Multiply the entire trinomial by that and subtract. Now I'm left with this. The biggest item out here is now bigger than what I have left. That becomes my remainder. So the biggest out here, my biggest power, which is at 2, is now bigger than that power, which is 1. If the powers were equal, or the power inside was greater, I continue with division. In this case, the power is 1, that power is 2, thus I am done. So I look up this item up here and write it there, and write my remainder as this divided by what I was dividing by in the first place. Moving on. Same thing here. I match x squared up with the 6x to the fourth, that's 6x squared. Multiply it to that trinomial, subtract. Now look, this is a negative 6x to the third. I multiply by negative 6x to my x squared because I need to get that negative, because I need to cancel. I need the opposite sign there. And subtracting a negative makes a plus. Subtract, oh, I can still continue here, that's a 4x squared. So I multiply x squared by 4 to that whole trinomial to get this, and then subtract. Notice there, that's a 5. 5 has no x, therefore it's less than what I was dividing by, so I'm good. And I write my remainder as such. Now I know this is not a factor of this because I have a remainder. If it were a factor, there'd be nothing left down here. Now, 15 is very interesting. State the end behavior. Again, x to the fourth. So as I put large values of x in, I get a large value of y back. Even if I put negatives in, a negative to the fourth power still gets me a positive y. List my p over q values. Now here's the problem I have. there is no p-value here yet. There is no constant term. So I must factor out the x first. That leaves me with this. There's my p. There's my q, the coefficient of x to the third. So factors of 30 divided by the factors of 1 gets me this. You also could put plus minus out in front of the whole list as long as you have parentheses. Neat conceptual question for C. How many total zeros should the function have? You always look at your biggest exponent. Biggest exponent is 4. That's the total number of zeros. Now find the zeros of the function. You do synthetic division with my p over q list. But remember, since I factored out that x, one of those zeros I already know is going to be 0 because you set each factor equal to 0. Now, if 5 is a 0, x minus 5 is a factor. If negative 2 is a 0, x plus 2 is a factor. If negative 3 is a 0, x plus 3 is a factor. And obviously if 0 is a 0, x is a factor. And then you would graph that as done in class. Same thing here. I do have a constant term at the end here, which is nice. I don't like to factor out a GCF. There's an x to the fourth out in front. It's the biggest power I've got. Put a positive to the fourth power, I'm going to get a positive. Even if you take a negative to the fourth power, I'm still going to get a positive. My p over q list, all the factors of 12, divided by all the factors of 1, there you go. Total number of zeros, what's my biggest exponent? 4. So that means 4 is the total number of zeros I could have. I'm not saying you have to have that many, but you could. Now, find the zeros of the function. That's synthetic division on my p over q list here, with these as my coefficients. 4, 3, 2, 1, x to the 0, no placeholders needed. My coefficients are 1, 4, negative 1, negative 16, and negative 12. Here are my zeros that I find. So if 2 is a 0, x minus 2 is a factor. If 3 is a 0, x plus 3 is a factor. If negative 2 is a 0, x plus 2 is a factor. And if negative 1 is 0, x plus 1 is a factor. And then you would graph accordingly using a t-chart for your missing values. You are now ready for the Chapter 6 test. Go henceforth and do.